So this video is on ionization energy. We're going to look at defining and writing equations for ionization energy and explaining how data from ionization energies provides evidence for electronic structure. So the general definition for ionization energy is the energy required to remove electrons from gaseous atoms to form gaseous positive ions. You can see in this diagram you've got the positive nucleus and the negative electron. So there is what's known as an electrostatic attraction between them. When you're talking about the attraction, never call it a bond. It's not a bond, it's an electrostatic attraction. So ionization energy is always an endothermic process, as it requires putting energy in to overcome this electrostatic attraction between the positive nucleus and the negative electron. So the greater the pull of the nucleus, the harder it will be to pull an electron away from the atom. This means the more protons in the nucleus, the greater the nuclear charge, and the harder it will be to remove an electron. So the more energy you have to put in to remove that electron. Generally, when they ask for the definition of ionization energy, they ask for the first or maybe the second or perhaps any number of ionization energy. So the definition of first ionization energy is the energy required to remove one electron from one gaseous atom to form one gaseous unipositive ion. You might see some other definitions talking about moles, but this is accepted for AQA. A common question is for the example is for them to ask you to write the equation showing the first ionization or the second, third, fourth, fifth, etc. of a particular atom or ion. So the way we do first ionization is you always have a neutral atom and it must be in the gaseous state. So make sure you include that brackets, little g. So you've got this gaseous atom turning into this gaseous ion, positive ion, plus an electron. You can see that electron was part of that. It's now split up into a positive ion and an electron. And if you don't include both the g's, you wouldn't get the mark. So if we look at hydrogen and helium, you can see down here, this is the energy required. This is the first ionization energy. So this is the energy to remove one electron from hydrogen. This is the energy required to remove one electron from helium. You can see that helium is almost double. So why is that? Well, let's have a look. So here's the electron. You can see they're both the same distance from the nucleus, the one that's being removed. But this one, there's only one proton, whereas for helium you've got two protons. So that by having two protons, it means it's harder to remove this electron. Therefore, the first ionization energy of helium is higher. If you compare helium and lithium, you might expect lithium to be greater. I mean, it's got 3 protons rather than 2, so you might expect it to take more energy to remove that electron. It actually takes a lot less energy, 519, and the reason for that is because the electron that's being removed, the first electron to be removed, is in this outer shell which is further away from the nucleus. So because it's further away, it feels less of that positive charge. It also has this what's known as shielding, so that the pull of the nucleus, this electron feels a shielding effect from these inner 2 electrons. So you can think the nucleus is positive, the electron's negative, and you have this electrostatic attraction between them, but it's weakened by the fact you've got these 2 negative electrons in the way, as it were, shielding this electron from the nucleus. You can think of, you may have learned in GCSE that these are called shells. We've also learned, looking at electronic configuration, they're also called energy levels. And this energy level here is the electrons that live in this shell, so shell number 2, exist at a higher energy level. So they already have quite a lot more energy compared to the electrons who live in the inner shell. So this means it requires less energy to remove them. I want you to spend some time now thinking about the patterns in ionization energy. So what do you think is going to happen as you go along a period? What do you think is going to happen to the ionization energy? Is it going to be harder to remove an electron or easier? As you go down a group, is it going to be harder to remove an electron or easier? So is the first ionization energy going to be greater or larger? And which elements do you think are going to be the one with the greatest first ionization energy and the least? So as you go down a group, we're trying to remove the first ionization energy. You're always removing the outermost electron. So in this case, this one here for lithium, this one here for sodium, this one here for potassium. So as you go down a group, you can see the trend is that the first ionization energy decreases. So that means that lithium, this one, is the hardest to remove, and potassium, that's the easiest to remove. And this is because mainly for two reasons. So this outer electron, it is further away from the nucleus, and it has more shielding. It has 3 shells in between it and the nucleus, so it is shielded from the nucleus. Whereas lithium has only 1 shell from the outer electron in between it and the nucleus, and also it is closer. This diagram here shows the trend in first ionization energy from with increasing atomic number. So here is hydrogen with an atomic number of 1, helium, lithium, beryllium, boron, carbon, etc., increasing in. So you can see this pattern, and we're going to go through this and talk about each sort of step individually now in the next few slides. But you can see the general trend is across a period. So here is the start of period 2. There's lithium all the way to neon. You can see generally it increases, but you have these 2 anomalies. And then here's period 3, starting with sodium to argon, again generally increases with these 2 anomalies. And you can see that the trend is as you go from, say this is period 1, period 2, period 3, you can see generally there's this decrease in first ionization energy. This is hydrogen, so hydrogen just has 1 electron. Here's the electronic configuration. If you remember we talked about comparing the two, you can see helium requires much more energy to remove that electron for reasons we already discussed. You see on this graph up the side you've got the energy required, so you can see helium requires more energy for its first ionization. Then, as discussed before, there's a big drop for lithium. Lithium requires less energy to remove this electron because of the shielding and increased distance. Okay, beryllium, you can see beryllium requires more energy because you have the same shielding, the same distance, but you now have increased by 1 proton. For AQA, they can often ask a 2-mark question saying, why is beryllium have a higher first ionization energy than boron? And the first mark is obviously that it has an extra proton, therefore greater attraction between the nucleus and the electron, but you must also mention the fact that they have the same level of shielding, the same distance. Now boron we would expect to be up here. It's got an extra proton, and in terms of shells, it's still in the same shell. The reason it's less than we expected, the reason it's easier to remove this outer electron, which is this one here, is because this outer electron goes into the 2p subshell. Now there's 2 reasons you can get away with saying for AQA why this is. The first reason is that the 2p subshell exists at a higher energy level than the 2s subshell. So that means this electron already has more energy, therefore takes less energy required to knock it off. The other reason is because this 2p orbital feels shielding from the nucleus from the 2s orbital, and also from the 2s subshell and 1s subshell. So carbon, as you might expect, adding another proton, so it increases. Nitrogen, again, an extra proton, therefore. Again, oxygen, you probably expect it to be somewhere here, because you've added another proton, therefore you've got increased nuclear charge, therefore increased attraction. But it's got this dip, and the reason for that is because the extra electron goes into this already half-filled orbital. You look here, see the 2p subshell. You add electrons, if you just start from here, you're adding an electron here, and an electron here, you're always adding it into an empty orbital. But oxygen, we're adding it into an orbital which already contains an electron. So you get electron-electron repulsion, which means that this electron here, let's see the one pointing downwards, that's easier to remove because it's getting some level of repulsion from the electron already in the orbital. Fluorine, increased proton, as you would expect. Neon, an increased proton, as you would expect. Okay, then there's this massive drop for sodium. Same reason from helium to lithium. So if you think about what's happened now, we're now in the free shell free. So this electron here is much further away from the nucleus. It's also now got shielding from both shell 2 and shell 1. So it's really, really much more easy to remove this electron. Magnesium, and then the trend for the next period is almost exactly the same as the second period. It's going to go up, down, down, up. Okay, so there's another thing called successive ionization energies. So they might ask you to give the definition, for example, of the second ionization energy. So this is the energy required to remove one electron from one gaseous ion with a 1 positive charge to form one gaseous ion with a 2 positive charge. You could be asked for any sort of number. You could be asked for the fifth ionization energy. So it's essentially exactly the same sentence, except you just replace the charge. So say we were asked to do for the fifth. So for the fifth, we're going to replace the word from this one with a 4, and we're going to replace the word where it says 2 positive charge to 5, because you're forming for the fifth, you're forming an ion with a 5 positive charge. So that'd be the energy required to remove one electron from one gaseous ion with a positive charge of 4 to form one gaseous ion with a positive charge of 5. So you might be asked to give the equation for the second ionization energy, or for the third, the fourth, the fifth. So for the second ionization energy, you can see that you're starting with a gaseous ion with a 1 positive charge. So here's the one for magnesium. You see it's a gaseous ion, there's the gaseous sign, with a 1 positive charge, forming a gaseous ion with a 2 positive charge, and again just removing 1 electron. This diagram here shows the successive ionization energies of calcium. So basically what this diagram here is showing, and what these numbers in here are representing, is basically, imagine you had calcium. Now calcium has 20 electrons, okay, and it's showing you the energy required as you slowly strip off those electrons. Now you think, as you strip off the electrons, it's turning into an ion. So the first electron is a 1 positive ion. By the time you get down to here, you've lost 19 electrons, so it's going to have a 19 positive charge ion. Now this data is really interesting, and it sort of proved the existence of shells and subshells, because what you might notice is there are these large jumps. So for example, if you look at the first electron, so removing the first electron takes 590 kilojoules per mole. Removing the second one is double, but removing the third one, it's a lot more than double. That's almost 5 times. So what's going on here? Well, if you think about it, if you look at the electronic configuration, you can see that the first 2 electrons were removed from the 4s subshell. So they're removed from shell 4. But this third electron, we're now removing it from shell 3. Now remember, shell 3 is a lot closer to the nucleus. It has less shielding, so therefore it's much harder to remove that third electron. Again, okay, as you remove more electrons, you can see that it takes more and more energy, obviously, because you're going up to higher positively charged ions. And you can see there's another big jump from 10 to 11. And again, look at the electronic configuration. All these ones here up to 10 have all been removing electrons from the shell 3. And suddenly there's a big jump for now we're removing electron from shell 2, which is again much closer to the nucleus, much less shielding. And again you see that same thing happening here at 19. We're now going into shell 1. It takes huge amounts of energy to remove those last two electrons. So read this question. It says, which has the higher value, the third ionization of aluminium or the third ionization of magnesium? And also I want you to try and think about the explanation for why. This is quite a difficult question, so pause the video. Okay, so the answer is that the third ionization energy of magnesium is a higher value. It takes more energy to remove magnesium. So let's have a look at why. So first off, we're going to talk about aluminium. So the third ionization of aluminium involves the following change. Okay, I'm just going to zoom in here. So you can see you've got an aluminium 2+ ion and is going to an aluminium 3 plus ion plus an electron. Okay, let's look at the electronic configuration. So you're going from, this is aluminium 2 plus, so you can see aluminium 2 plus has got 1 electron in shell 3. Okay, and then so you're removing, that's the electron you're removing. Okay, now let's look at compare it with magnesium. So the magnesium, the third ionization of magnesium is involved, again, the following change, pretty similar. You can see you've got, again, exactly the same. It's a 2 plus ion going to a 3 plus ion. But let's look at the electronic configuration. This is where the sort of answer comes in. So if you see the electronic configuration of magnesium, it is 1s2, 2s2, 2p6. So the electron that you're removing from magnesium is in shell 2. The electron that you're removing from aluminium is in shell 3, so which one's going to be harder to remove? Well, it's going to be the one in magnesium, because the one in magnesium is closer to the nucleus and it has less shielding. So therefore it requires much more energy to remove an electron from magnesium 2 plus than aluminium 2 plus. So you can just have a read of this if you fancy. This is sort of a exam style answer to what we just talked about. So pause the video. Okay, another difficult question. Which has the higher value, the first ionization of sodium or the second ionization of magnesium? So pause the video. So the answer is, it's the second ionization of magnesium. Okay, so let's have a look. So first ionization energy of sodium involves the following change. So you're going from a neutral atom to a 1 positive ion. Okay, in terms of electronic configuration, that's where the answer again lies. You can see you're removing an electron from shell 3. Okay, now let's have a look at magnesium. So magnesium, the second ionization of magnesium involves this change. You're going from a positive ion to a 2 positive ion. Okay, and you can see that actually, in terms of the electronic configuration, it's actually removing from the same shell. So why is magnesium greater? Well, what's the difference? Well, for magnesium, you're removing your electron from a positive ion, whereas from sodium, you're removing an electron from a neutral atom. So that's your difference. Your main difference is the fact that magnesium, as it has more protons, and it is a positive ion, the nuclear charge is greater, and it's able to hold on to that electron with greater strength. Therefore it takes more energy to remove it. So I suggest you go, there's if you haven't already checked it out, it's a really great website called, I think it's just A-Level Chemistry. Type A-Level Chemistry into Google, it's the first one that's going to come up. If you go on to AQA, Unit 1, and look at exercise 1.1, exercise 4, it's got some really good questions on ionization energy, and it's also got the answers